So, yeah, all of that, all of the stuff you guys have learned up to now, leads us into cloud formation. We're going to talk about fog. We're going to talk about different types of precipitation, frontal systems, things like that. So you guys have learned the base work and the very micro detailed information as to what creates the weather. And now we're going to talk about how it reacts and what happens when, the dew point and the temperature spread converges, things like that. So let's talk about some clouds. So this is kind of a fun. I like talking about the clouds. A lot of people really have no idea anything about clouds other than some look fluffy and some bring rain and some look like, call them mare's tails and stuff like that. So it's kind of fun to learn the different types here. So as you can see here, we've got 4 basic cloud forms. Okay. The first one is Cirriform Clouds. These are usually high-level clouds. So these are the ones that are way, way up there. They call these mare's tails. There's a couple other names, but just high-altitude clouds, okay? They're thin and wispy. And a lot of times what it represents, like when we see those, the reason why they're so thin and wispy is because generally, it means that there are really strong winds at those higher altitudes. So Nimbus clouds. These ones are the ones that we can associate with rain, right? So these are the heavy black clouds, dark gray clouds, typically lower in elevation. So between 7 and 15,000 feet, brings steady precipitation. As the clouds thicken, the precipitation begins to fall, and the base of the cloud tends to lower to the ground. So nimbus, like it says, means rain. So we can have like a cumulonimbus, we can have a stratonimbus. The nimbus just means that the cloud type that you see is bearing rain, like it's going to rain, right? And like anything scientific, we just combine Latin words to make, and the Latin meaning of the word forms the just kind of like glues it all together, right? Like when we talk about cumuliform clouds, cumuliform cloud, or I'm sorry, when we talk about stratus, stratus is Latin for layer or blanket, right? So when we say stratonimbus, we've got a layer cloud bearing rain. Okay, kind of makes sense, right? So cumuliform clouds, these are the really fluffy clouds, like the Care Bear clouds. Can get these clouds can get extremely tall in elevation. One thing that we see a lot of that's associated with this type of cloud is turbulence. And that's due to the fact that that's how these things are created, is a rapid rise of air that causes that water vapor to kind of like create those cotton ball looking clouds. So it's typically you got a lot of convection in these clouds that build it in altitude, and that convection or that churning force in that cloud, that's what's causing the shape. So when you fly through these clouds, you're going to feel a buffet, you're going to feel turbulence. So stratiform clouds, these are pretty calm clouds, like when you have ceilings and stuff like that, a lot of times they're going to be stratiform clouds. And it's just like it says, it's like a blanket, right? These stratus clouds are pretty nondescript clouds. They just kind of blanket the sky. And typically they're low layer clouds. So here we talk about cloud levels. Typically clouds are divided into three classes. You got a high, middle, and a low class. Sometimes these cloud layers will overlap one another, but typically, in our temperate region here, where our high clouds are considered anywhere from 16,500 feet to 40,000 feet. Our middle clouds, 6,500 to 23,000 feet. And then our low clouds are the surface to 6,500 feet. So, this is just a very generalized number here. This number here, super generalized. I've seen clouds hit 65,000 feet in the temperate zone. So it just depends on how violent the storm is. Some of the recipes in creating these clouds, can make the clouds a lot taller than that. So in each one of these levels, high, middle, and low clouds, we can divide the clouds by type. Clouds, when we talk about ceilings, so this is what forms our ceiling. Clouds, let's see. So they're identified based upon one's observation point in a particular elevation from sea level. One might observe stratus clouds enveloping the top of a mountain. However, on the top of the mountaintop, one would observe and report the same cloud as fog. So it's kind of based on perception. The important thing to know about like cloud types and elevation is whenever we look at our weathers, our different weather forecasts, or what's currently happening. Typically, we have a station near the airport, right? And what it's doing is it's measuring the base of the clouds, okay? So, we may have like this fluffy cumulus cloud. The number that we're concerned about is how high above the ground the bottom of this cloud is. Okay. So from here to here, that's what number we need to know for determining legal to go. Do we need an alternate, right? So that's what we're concerned about with cloud types and cloud levels and things like that. So high clouds, like I told you before, these are going to be Cirrus clouds. You can see here that we've got several varieties of Cirrus clouds. We've got just plain Cirrus, Stratocumulus, and Cirrostratus, right? So the Cirrus cloud is composed of detached elements from in the form of white, delicate filaments of white. So these are our mare's tail, just really fine, wispy. Many of the ice crystal particles of the cirrus are sufficiently large to acquire an appreciable speed of fall. Therefore, the cloud elements often trail downward into well-defined wisps called mare's tails. So they have very little effect on aircraft and no significant icing or turbulence. But generally, these are a sign of, like I said, high-speed winds, okay? That's why they're so wispy like that, is because of the wind. It's kind of like thinning it out, So cirrocumulus clouds.
If those clouds are an indication of high-speed wind, so wind does not necessarily cause turbulence?
Correct.
And are these kind of like narrow winds, or do they kind of tend to be across broad fronts? Or
no, it's the winds are going to be over a huge area. It's going to be generalized over a huge area. So, whereas like down at the surface, you may see like a cloud that's kind of like thick and dense and like that, because of the high speed winds, it just kind of thins it out and stretches it over a long part. It's like a painter taking a blob of paint and then, streaking it. It thins out as the artist gets away from the blob of paint. Does that make sense?
Yeah.
So that's generally what we see with these cirrus clouds. Is typically there's really high speed winds, and winds aren't what cause turbulence. What's causing turbulence is you have these pockets. So you have, let's say, there's a couple different types of turbulence, and we'll talk about it more. But you may have like a mountain here. Okay, as the wind comes up, it rises really fast, but then it'll come down here and it'll fall really fast, and so you get this wave. It's weird. We call it mountain wave turbulence, but for miles, you're gonna feel this wave, right, of turbulence. So that's one way. And typically, mountain wave, the only time we experience that is when we're like on approach to land. Don't get a whole lot of mountain wave up at higher altitudes. The stuff that we get at higher altitudes a lot of times is caused by thermal pockets. So here's the ground. You have this column of heated air. And it's rising faster than the air around it. So when we fly through that column of air, we ascend really quick, and as soon as we hit the other side, we descend a little bit. So these columns of air may be fairly small, and so that's why, and you have several of them, so it kind of is like a washboard in the sky. Does that make sense?
Yeah, it does actually. So it's not so much air or wind moving in a consistent pattern, kind of parallel to the terrain. It's the wind where the terrain gets bumpy and then the wind's going over it, or where there's vertical air movement, not so much the horizontal movement.
Yeah, and it's not necessarily vertical air movement. It is. We call it a thermal.
Okay.
And it's like...
Is it kind of like bubbles?
Yeah. Well, yeah, kind of. But it's... And it's kind of hard to explain. We'll get into turbulence, and we'll talk a lot about turbulence. But another thing that happens is we have the jet stream. And the jet stream is a cylinder of air. It's like a tube, right? Like right here, the wind's going 150 knots. And on either side, it's going 50 knots. So we have this really fast column of air sitting between two slower speeds of air. And sometimes when we're crossing it perpendicular to it, this is one that we associate with wind. When we're crossing the jet stream, you'll get turbulence. And that's because you're going from like a lower speed to a really quick speed, so it gets really bumpy as you go through it. But if you get into the jet stream, into this tube of air, then it tends to stay fairly calm. It's just when we're crossing it, it kind of, you got wind that kind of like bubbles over it, kind of like a truck.
Okay.
I don't know if that makes any sense. You got a truck here. It's got the bed. Super awesome looking truck. Anyways, as it comes over the top, you get this cylinder of air here. Think of this as like the jet stream. Everything going over kind of is bumpy, but then you have this round column, like cylinder of air, an air pocket. So, but we'll talk about a lot of turbulence. But because turbulence can be extremely dangerous. But anyways.
Okay. No, I was just I didn't realize that there were actually clouds that were like, okay, if you're flying in these clouds, it should be a nice flight. So
yeah, there are. And stratiform clouds. Stratiform is very calm, smooth air. They're an indication of very calm, smooth air. So we'll get to that. But anyway, so Cirrocumulus, it's a cirriform cloud appearing as a thin white patch sheet or layer of cloud without shading and is composed of small elements in the form of grains, ripples, etc. So here's what cirrocumulus clouds look like. It's like popcorn, is what I've always called it, like popcorn clouds. Really high altitude, really bumpy. These ones, now remember, we're taking cirro, which means like higher altitude. And we're taking cumulus. And when I said cumulus, you remember how I was talking about how it's a sign of like bumpy air. You've got these, you got convection in those clouds that's causing the air to be bumpy. These high altitude clouds do indicate turbulence. Like it's going to be bumpy right there. Okay. Super cooled water droplets. Pilots can expect some turbulence and icing. There you go. So Cirrus Stratus. Okay. Appears as a whitish veil, usually fibrous, like hair-like, but sometimes smooth, that may totally cover the sky, and often produces a halo phenomena. So, like I said before, stratus means layer or blanket, right? So, and stratus clouds don't produce a lot of turbulence. So you can see we get these clouds a lot, especially up in Salt Lake. It's just kind of like a thin blanket, really high altitude, calm, smooth air. And can make for kind of a dreary day, I guess you could say. But yeah, so thin white blanket at high altitudes, like it says here, composed primarily of ice crystals and contain, if any, icing and no turbulence. All right, so let's move down to the middle clouds. We call these alto. Okay, we got Alto Cumulus, Alto Stratus, Nimbus Stratus. These are our mid-level clouds. So remember, middle layer clouds typically are 6,500 to 23,000 feet. Alto Cumulus, okay. White or gray in color, occurs as a layer or patch with a waved aspect. So pilots can expect turbulence and small amounts of icing. Okay, so this is what it looks like. Looks a lot like the Cirrocumulus, right? It's just at a lower altitude. It's kind of cool with these Alto Cumulus clouds. What happens is as planes fly through them, it punches holes, which are really cool. So you'll see these holes appear where aircraft are coming down through the cloud layer for landing, like typically on approaches. When you have alto cumulus clouds, you'll see this. It's pretty cool. I've seen some really neat pictures of it where you can see like multiple little ripples, I guess you could say. There you go. See, this is where the airplane's coming down. So the air, so the planes are coming through in this direction. The air kind of sinks below it. So, like, think of it as placing a ball on a sheet or something of that nature, and how it kind of like does an impression. That's what happens when airplanes fly through those clouds. And it's funny too because, oh, excuse me, people like, oh my gosh, it's a UFO, government's killing us, stuff like that when they see it. So Alto Cumulus lenticulars. So these are very dangerous clouds. ACSL, this is one of the few clouds that we're going to see in our weather reports, okay? Alto Cumulus standing lenticulars. These clouds often appear over mountains or hills, and they are a lens shape. You remember how I was talking about the mountain and the winds coming up really fast and then dropping really fast? That's how these are formed. What will happen is the wind comes up, there will be clouds, low layer clouds, and as the winds come up, they'll smooth out this side of the clouds, and as they come over the top of the mountain, they smooth out the other side. So you get this lens shape. Some pilots call them pancakes. You can have like double, triple stack pancakes. That's kind of... There you go. There's a double stack for you. There's probably a mountain somewhere down here. But yeah, expect severe turbulence. That is insane right there. That is what I'm looking for. This is the best picture you could ever use to describe an alto cumulus standing lenticular. This is like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 stack pancake. You don't want to be flying anywhere near that mountain by like 50 plus miles, because you're going to get tossed around like a rag doll. Yeah, super cool. Yeah. Clouds are just cool in general. There's another good example. Alto Cumulus standing lenticular. That's a tornado. The start of a tornado, at least. But yeah. So the cloud elements form at the windward edge of the cloud and are carried to the downwind edge, where they evaporate. The cloud as a whole is usually stationary or slow moving. These clouds have very smooth outlines and show definite shading. So it says that it's not necessarily an indication of turbulence. Yeah, yes and no. I mean, there are other elements that help form the turbulence, the mountain wave turbulence, but at the same time, it's a very good indication, and that's why they put it in the METAR, is because when there's an Alto Cumulus standing lenticular, generally there's going to be moderate to severe turbulence associated with it. So alto stratus, cloud type, form grayish bluish, never white. Very often totally covers the sky, may in fact cover an area several thousand square miles, layer parts thin enough to reveal position of the sun, and if gaps and rifts appear, they are irregularly shaped and spaced. So just like a hazy, bluish gray, really, really dull day. That's typically what we're seeing with our alto stratus. Calm, smooth flying. One thing that can be scary is that they hide cumulus clouds really well. If you're below the cloud layer, you'll have patches of cumulus clouds. So if you're flying at lower altitudes, you may fly into some nasty turbulence without even knowing. But typically we're high above the clouds, and it's not a big deal. So it's like Salt Lake in the wintertime when it's not inversion. So low clouds, we've got cumulus, towering cumulus, Stratocumulus, stratus, and Cumulonimbus. So the cumulus and towering Cumulonimbus, or towering cumulus clouds. So, like it says here, appears as rising mounds, domes, or towers. The upper parts, which often resemble cauliflower, sunlit parts of these clouds are most brilliant white, and their bases are typically relatively dark and nearly horizontal. So they're like, you can see that a lot of the cloud bases are going to be pretty flat, but the edges and the tops are all fluffy, powdery. Okay. Pilots can expect some turbulence and no significant icing. However, towering cumulus clouds, pilots can expect very strong turbulence and some clear icing above the freezing level. The towering cumulonimbus is also an indication of impending doom, thunderstorms. I flew into Denver earlier this year, and it was crazy. There were massive towering cumulus clouds all over the approach. The pilot did a lot of cloud dodging going in. Just because it was so turbulent. And we hit some pretty good bumps still, and we did have to fly through some of them. But it was pretty neat looking outside the window as we were flying through it. Let's see if I can find one of my pictures. So yeah, this was as we were coming into Denver. It just looked like this all over the place. You know, that's a good 10, 15,000 foot cloud. And you can see how it's starting to, we call it anvil at the top there. And you can see this is a really good example of a thunderstorm or a towering cumulonimbus cloud, because you can see that on this backside here, like down in this area and in here, where it's starting to anvil out. This is the mature stage of a thunderstorm. Well, it's almost to the mature stage of the thunderstorm. So we've got the cumulus, then we have a mature stage, then we have a dissipating stage, okay? So you got the cloud here, and the thunderstorm doesn't happen, like rain's not dropping out on this side, the rain drops behind the cloud. So you get a lot of rain, precipitation coming out the back here. You'll also see hail a lot of times, you know, out this side of the cloud. But the hail, one thing that's kind of crazy about hail is sometimes these clouds build so fast, and the way hail forms is like rain falls down here, and then it'll get close to the bottom of the cloud and it'll warm up, and as it warms up it turns back and it climbs to the top of the cloud, and then it cools and turns into ice, and then it falls back down, comes down here, and it just keeps doing this pattern. And each time it goes to the bottom of the cloud, it gets another layer of ice on it. So the hail gets bigger and bigger and bigger until the cloud can't hold it anymore, and then the cloud spits it out the back. And so they've seen hail fall as far as 40 miles behind the thunderstorm. It's pretty crazy. Think of these clouds as a giant washing machine. If like a little tiny Cessna 172 decided he was going to be awesome and a lemming, I guess you could say, and fly through this cloud, he would probably come out as little chunks of metal on this side somewhere. Like pretty dangerous clouds to fly through. And it's just that churning motion, that convection. Just it's a nonstop churn that creates these clouds. So we also have Stratocumulus. They're predominantly stratiform, but it always has parts, dark parts that are non-fibrous. Let's see. Giving them the appearance of a simple or occasional across pattern wave system. So here you go. Those are Stratocumulus, still pretty calm. Pilot, you get a little turbulence, but nothing crazy. And you usually get better visibility than these low stratus clouds. So stratus clouds, not usually producing precipitation. Usually if they do, it's pretty small particles or snow grains. Yeah, like it says here, stratus produce little or no turbulence. They can be hazardous if it's like really cold outside because of icing, right? What do we have to have? What are the conditions for icing? Who can tell me that?
Isn't it like 40 degrees and just moisture in the air?
So 10 degrees Celsius and visible moisture. So in aviation, we use Celsius, like.
Right. 10 degrees is 40. Oh.
I thought we figured it out to be like 52 degrees or something like that. But yeah, it's that's the one thing that we do. And like I said the other day, I think it was Tuesday, we use, it's weird because we kind of like use a combination of the metric system and the standard system. So we use Celsius, don't use Fahrenheit, but we do use like standard, like miles and stuff like that. So low layer stratus clouds. It's just that gray blah sky. Usually we're going to have low visibility or low ceilings due to this cloud form. So stratus fractus or cumulus fractus, signs of bad weathers. Ragged shreds of low clouds always appear in association with other clouds in a short time before, during, and a short time after precipitation. Okay. Cumulonimbus. So cumulonimbus, it's a cumulus cloud with rain. And as you can see here, this one hasn't anviled out like that picture I was just showing and kind of talking to you guys about. But you can bet your britches that it's raining like cats and dogs underneath that cloud. Okay, so it's still forming into that towering cumulus stage, where the most violent, thunderstorms. That's when we get the most violent thunderstorms. So this is after it anvils. And you can see why we call it an anvil top, because it looks like an anvil, right? These clouds, or these towering cumulus, are so dangerous to fly through that typically air traffic control will keep pilots away by at least 20 miles. Like it says here, Cumulonimbus contains nearly the entire spectrum of flying hazards, including extreme turbulence. Okay. So precipitation. Basically, you've got this water vapor droplets all around, right? All these little specks of water droplets, water vapor in the sky. Well, what happens is they start falling, and as it falls, more of these little small cloud or rain droplets kind of attach themselves to it until it forms a water droplet, which we call rain. Sometimes what happens is this rain evaporates before it hits the ground, and we call that, whoa, that's not at all. Virga. I spelled it wrong. Damn it. Sorry about that. Hopefully I caught it before everybody saw the Spanish word. Okay, there you go. Virga. Not Verga, Virga. So, basically what's happening is the cloud is raining. It's dropping this rain, but before the rain hits the ground, it's evaporating back up into the cloud. So, so we have a lot of different types of precipitation. You've got snow, which there's just a deep cold layer, and the rain stays frozen the whole way down to the ground. You got ice pellets where they kind of, you've got a cold layer up near the cloud, cold layer down near the ground, but you have this shallow pocket of warm air that melts the snow. As it melts the snow, it kind of turns it into that ball shape, and we get the ice pellets, right? Or snow grains. Something we also refer to it as. Have freezing rain, where you have cold layer up in the cloud, deep warm layer, and then a cold layer. So it turns back into a liquid state, and then from the solid to the liquid, but then it's cold enough to where it, as soon as it hits the ground, it's like a super cooled water droplet. As soon as it hits the ground, it freezes instantly and turns back into a solid. Then you got rain, just deep warm layer all the way down to the ground. One thing that I want you guys to look at is, so we're going to talk about METARs coming up here. And I'm going to give you guys a head start. On this, because you guys need, you have to know how to decode these. Um, let's see here if I can find the. Excuse me. Ah. Where did it go? Anyways, this has it too. What I need you guys to start learning is this right here. Okay, super, super important. Make flashcards of each one of these and go to town. You might even be able to look on Quizlet and look at like do a search for METAR codes or something like that, and use Quizlet on that. I'm sure somebody else has already made a deck of flashcards for it. But make sure you have all of these memorized. So if you see a negative sign, that means that it's light. If you don't see anything, it's moderate. And then if you see a plus, it's heavy. VC is in the vicinity. All of these right here, like you have to have these memorized because you will be asked on every interview. You spend a heck of a lot of time decoding METARs and TAFs. As a dispatcher, so on and so forth. So please, 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 please memorize all of those.
Can you copy and paste that link into the chat box?
Yeah.
There you go. But yeah, super, super important. Start looking at this because you guys are going to do a lot of METAR decoding. We'll just help you guys. But that pretty much ends the stuff from last night. So. Let's do a 10-minute break. Does that sound good?
Yep.
All right.
Sounds good.
All right, so you guys ready to dive in today's fun?
Yeah.
Okay, we're working our.
So let's watch this first video. It's 10 minutes long. And it's going to talk about fog. So everybody jump on, watch the video, and just, yeah, you guys know the routine. All right. Is everybody through the video?
That guy sounds like Obama. He reminded me of Obama the way he talked. I like couldn't get over it. Like, God, it's like just the way he talks. Like the style sounds like Obama.
That's awesome. I've never thought of that. So, that was a super good, thorough enough overview of fog. So, radiation fog, as you remember, very light winds. And like it said, the temperature is falling to meet the dew point. Okay, so do you guys remember what the dew point is? You guys talked about it last night. You guys remember?
It's like when the air is 100% saturated.
Yeah,
and
it's
represented by a temperature.
Yeah, so it's the temperature at which the air reaches 100% saturation. Does that make sense? So the way we see it is in a METAR. My gosh, I can't type anymore. So let's do Salt Lake City here. All right. So Salt Lake City METAR. Right here we have our temperature dew point spread. So it's currently 31 degrees Celsius and the dew point is -2. Okay, so the temperature would have to drop to -2 to reach 100% saturation. Okay, or the dew point has to rise to 31 degrees in order to reach 100% saturation. So when we see the temperature and the dew point come together, so if it was 31 and 31, we know that there is likely fog. And the way we confirm what type of fog is a lot of times we can look at the wind and go, that would have to be advection fog. Because, that wind speed is actually probably not going to see a lot of fog happen with wind speeds like that. But advection fog, remember how he said, is typically going to be somewhere in the 10 to 17, 20 knot range. Okay. So, yeah. So, like I said, either the temperature has to come down to the dew point or the dew point, or also you can think of it, the content, the water vapor content of the air has to come up to the 31 degrees in order to create fog. So it's one or the other or a combination of both, like both of them coming and meeting together. We call that the temperature dew point spread. Okay, so radiation, light winds, and the temperature falls to the dew point. Okay. It burns off really quick. That's something that is important. We see a lot in the winter. You'll see a lot of radiation fog throughout the United States. You'll see a lot of areas go down to like a quarter-mile visibility. And it's typically when we are looking at our software, they got this map of the United States here. You know what I'm saying? We call it like a daylight shading. Okay, so when the sun is first hitting a city, let's say Dallas, Texas. Okay, you got the great state of Texas here. Okay, when the sun's first hitting Dallas, Texas here, typically that's when we're going to see the fog appear. Or even at night, sometimes we'll see the fog kind of set in, right? But as that daylight shading, as the sun's been on it for an hour or two, you'll see that fog just disappear and it'll be clear skies. Okay, so it burns off really quick. Doesn't take much warming to make the fog disappear. Advection fog, this is the type of fog we see in the Bay, San Francisco, like every single day during the winter and spring. Yeah.
Garrett, sorry, was unable to get off mute. Back with the radiation fog. How thick and how deep? I mean, how dense and how deep can it get?
It's typically fairly thin, so we're talking like 60 feet thick, but it's enough to obscure visibility drastically. Okay. So it's thin layer, but it's very dense.
Okay. Because I was just trying to figure out, I used to spend a lot of time in the Central Valley in California, and they would get a fog in there that would basically, it could stretch for as far as 600 miles.
Yeah.
Cover the entire Central Valley, and it was just, it sounds like it's radiation, but I'm not 100% sure because that stuff is just strange. It doesn't necessarily burn off during the day.
Yeah, it
does happen pretty much in colder months.
Yeah, that's advection fog here. So advection fog is what we're going to see along the coast of California most days, especially during the winter time. And it's associated with light to moderate winds, up to 15 knots, sometimes even up to as high as 20 knots. Okay. But it's formed a lot like radiation fog. The temperature drops down to meet the dew point. And we also call it sea fog, but basically the amount of water vapor in the air is extremely high. So it's got a high dew point, and then we have the warmer temperatures. When they converge, we get this sea fog, and it's kind of like a convection oven where it just kind of like blows, or I wouldn't say convection oven, but it moves in really rapidly over the coastline especially.
Well, and I guess the follow-up question after that is the Central Valley is cut off from the coast by a fairly decent mountain range. So can the winds like that get over a 5,000 or 6,000 foot mountain ridge?
Yeah, the water vapor. I mean, there were days when I was living in Rancho Cucamonga. We'd still get extremely humid days, you know. It just depended on which way the wind was blowing. And but we would get heavy, dense thick fog, even up, against the Santa Ana Mountains there. So, yeah, it definitely can be pushed deep into the inland, I guess you could say. And even lakes can produce enough water vapor or dew point to produce the same effect. But these ones, California is pretty notorious for the advection fog. And because of the winds, it can reach far distances. They, very widespread. This, it tends to be very thick. We're talking hundreds of feet thick and just super dense.
Okay. Yeah, because I remember, are you familiar with the Grapevine where the I-5 crosses the mountain?
Yeah.
Into the valley? I was driving that one time and I was coming, basically you had to get a good 500 to 700 feet above the valley floor to get rid of it, to get clear of it. It was just amazing stuff. It was like you basically were following a cop, and if you couldn't see the lights, you were supposed to stop until you could see the lights again.
Oh, wow.
It was insane. I think visibility was like 30 feet.
Yeah. Yeah, it can get extremely scary really quick. And it's even more scary for airplanes, because fog obscures the airport altogether. You're solely relying on instruments at that point,
Yeah, I know that there's not a lot of high traffic in Bakersfield, Fresno, all those airports, but basically everything from Bakersfield to Oakland was closed.
Yeah. Yeah, and that, we do fly into those places still. A couple times a day, we'll fly into Fresno or, Bakersfield, I think. What's the airport in Bakersfield? I'm trying to remember.
Don't remember, but yeah, there's both a Delta and United service there. So
yeah, we have a couple flights a day go into each one of those areas. Even it's crazy because you'll see the fog roll into like San Diego, and then you'll see LA go out and Santa Barbara. You'll see that entire coastline just trickle up where the visibility will just go to crap. And it's typically the advection fog that's doing it. So it's the moist air travels against the cold surface, bringing the temperature and the dew down to the dew point, which creates the fog. See this? This shows you how far it can spread. Moist air from the Gulf of Mexico spreads northward over the cold ground. The fog may extend as far north as Great Lakes. So we're talking thousands of miles that it can extend. And it doesn't burn off the same as radiation fog. Like there's certain cities where you're like, oh, that fog will be gone, in 40 minutes. And it'll be gone in 40 minutes. There's some when it hits San Francisco, it's like, well, next 4 hours are shot, just prone to that advection fog. Upslope fog, this is what we get a lot of in Utah. Colorado, Rockies, get a whole lot of upslope fog. So it's just moist, stable air being adiabatically cooled. So adiabatically, what it means is that as it gains altitude, as the wind pushes it uphill, the dew point or the temperature cools as we get higher, right? Remember, we talked about this. The standard is 2 degrees Celsius per 1,000 feet. Okay, so as it's moving up this mountain face, the dew point may be 10 degrees Celsius down here in the valley, but and the temperature may be like 21 degrees Celsius. So temperature 21, dew point 10. But as it climbs the mountain, it gets colder and colder and colder until the mountain until that moist, stable air hits that layer, in which the temperature drops down to the dew point, right? And so once we hit that, then we get this nice cloud formation that happens on our mountain ranges. Fog. It looks like clouds, just really low clouds touching the mountains, but it's actually called upslope fog. So let's see. So you can see it, like, here's a good picture of it. You can see where, on this picture especially, you can see where the temperature and the dew point converged, right? Up above it, it's colder, so the temperature is less than the dew point, right? So you just get this layer where the temperature and the dew point are converged. Pretty cool stuff. This stuff will blow out or burn off. Yeah. It can burn off or blow out fairly quick, especially because mountainous terrain. Typically, we get a little more windy when we're in the mountains, right? So it doesn't take much for them to all of a sudden disappear, like the upslope fog to disappear. Frontal fog, don't care. I mean, it's just like radiation fog or any other fog. Radiation or advection fog, as the warm air gets pushed up along the front, and the cold air converges, it traps the fog down below the pocket of warm air. So there you go. Steam fog. So steam fog is kind of crazy. Like he said, thunderstorms. You have a thunderstorm move over and water accumulates in a parking lot, and it's a nice warm day, and all of a sudden the thunderstorm cools the day off by like 15 degrees, and now you've got a ton of moisture in the air. It's pretty common to see steam fog. Steam fog's really thin and light. Typically not a big deal. And then it goes away pretty quickly. Then ice fog, like it said in the video, you have to have super cold temperatures, and it sucks. Like ice fog is just bad juju and for aviation, but it also sucks when you're just walking outside because you get like ice crystals in your nose and stuff. I remember in basic training when I was in the Navy, like it was a sunny, bright day, super clear, and they would come up over the intercom and they'd tell us, basically they'd tell us what uniform to wear for the day, what level of uniform. So there are different levels of how many layers you wore. And like the highest level, we would wear like a beanie. We looked like ninjas, right? In blue camo, which is really funny in and of itself. But we looked like ninjas, where we'd have a black beanie on, we'd have a face mask on, have a turtleneck on, and then we were bundled in both layers of coats. Anyways, that was the first time I walked outside and it was negative 40 degrees outside. Bright sunny day, thinking it's going to be nice and warm. Nope. Walked outside, negative 40 degrees, no wind, ice fog, and my eyelids, I blinked when I got outside. I blinked and my eyelids froze together. I had to like pry my eyes open again. It sucks. Chicago sucks, by the way. I was there too long and during the worst part of the year. So icing, my pilots have probably been indoctrinated with icing because icing is super bad for airplanes. I know we've talked about it before. So we got another video on icing. Oh, no, we don't. Thought we had one. Oh, well. So let's talk about icing real quick. Okay, so we've got 3 different types of icing. So icing, what it is, are super cooled liquid droplets that as soon as they make contact with the aircraft, they instantly freeze. We talked about the water bottle that's like really cold and you pour it onto a metal plate and it instantly turns to ice. Yeah, that's super cool, super cooled water, right? So structural icing, the way it happens is the plane hits those super cool droplets and boom, ice. We got 3 types of ice. Super important, write it down. Test question, hint, hint. We have rime, clear, and mixed ice, okay? Depending on a couple of things determines how or what type of ice we're going to see on the aircraft. So rime ice is rough, milky, and opaque ice formed by the instantaneous freezing of small supercooled water droplets as they strike the aircraft. Okay. These are jagged. It's grody looking on the plane. Super, super bad. So here you go. That looks like snow. There you go. There's some rime ice. Ooh, there's some rime ice. Bad crap. There you go. That's a good example right there.
I've seen it on some airplanes where it blocks most of the view of the pilots on the windshield
Yeah,
when they come into taxi.
it's not good stuff. And before they take off, they have to de-ice, is what it's called. But they won't de-ice the windshields because it jacks up the windshields. They only de-ice the leading edges of the wings. Well, they de-ice the wings, I guess I should say. So there's your rime ice, okay? Here's your glazed. You can see it's a lot clearer. Clear ice, glossy, clear, translucent ice formed by the relatively slow freezing of a large supercooled water droplet, okay? So what happens is as it strikes the aircraft, it's not quite cold enough yet, but as the air pushes the droplet back, it freezes. So it like kind of drags out. Rime ice instantly freezes, and that's why it gets that. It's got a lot of air and it's opaque. That's rime ice, right? So glaze or clear ice, it hits the aircraft and it kind of like just moves back across the wing of the aircraft. Sometimes you have pretty long runs of this clear ice that kind of wrap around the wing. It looks more like frost. It's probably a little too small to see. Dag nabbit. I love it when people put miscategorize things on here. Anyways, you guys get the point, right? Clear ice, translucent, turns into ice as it moves back on the aircraft wing. And then we have this mixed ice. So mixed ice is just a combination of both rime ice and clear ice. Okay. So icing factors. Structural icing is determined by many factors, the meteorological quantities. Most closely related to icing type and severity are in order of importance. Supercooled liquid content, temperature, and then the droplet size. So ice potential is very temperature dependent. For icing to occur, the outside air temperature must be below 10 or below 0 degrees Celsius. But we know better than that when we say that icing is 10 degrees Celsius and visible moisture, right? So that could be a cloud, that can be fog, that can be rain, it can be mist, it can be snow, whatever it is. If there is any moisture that is visible in any way, shape, or form, and it's 10 degrees Celsius or less, that's the potential for icing.
And what's the acronym SLWC?
SLWC stands for supercooled liquid water content. Oh, yeah. Supercooled liquid water content. We'll ignore all this temperature stuff because I don't want you guys getting confused. Small droplets tend to impact the airfoil near the plane's leading edge. Large drops, including freezing rain and freezing drizzle, can cross the streamlines and impact further back. So if we have larger droplets, so small droplets, they hit our anti-icing equipment and they're done, right? It like zaps them out of the air. The problem is when we have larger supercooled water droplets, they will hit that leading edge and pass the anti-icing equipment. That wing is still freezing cold, right? So that water will impact on the front. It will melt instantly. There won't be any cause from that, but as it rolls back on the wing surface to that super cold wing, it can get past our anti-icing equipment. Okay, so it can be pretty dangerous, even though we do have the anti-ice. So there's two types. One thing that we need to talk about is there's two types of anti or de-icing equipment on aircraft. Anti-ice means that ice is not even allowed to form, right? And that's usually going to be like they're going to have a heated leading edge. So that's what our CRJ 700 has, is that chrome edge. That's a heated. It's heated with the engine exhaust, right? Our bleed air. Some aircraft have a black, they call it a boot, on the leading edge of the wing. And what it does is it doesn't prevent the ice from forming on the wing, but when the aircraft gets a certain amount of ice on the wing, that black rubber leading edge will inflate and expand rapidly and break the ice off of the wing. And we call that de-icing. So it will allow the ice to form still, but it like pops it off. Does that make sense? It's kind of like hitting the ice tray against the counter. So two different types on how aircraft manage icing conditions. De-icing fluid is different, okay? De-icing fluid happens on the ground only. And if any of you have flown, you guys have seen during the wintertime, you've probably seen or been in an aircraft that has been de-iced out on the pad, right? So they take basically an antifreeze and they'll spray it all over the wings, the tail and the wings. And what it does is it doesn't allow ice to form on there for a certain duration of time, depending on the type of liquid that's used. We can extend how long we have to take off. Once we're in the air, the anti-icing equipment is working and it's keeping the ice off the airplane for the most part. 90% of the time. 99% of the time. But we have what's called a holdover time with our de-icing fluid. So there's like 4 different types of de-icing fluid. And they can either be cold or hot. And they'll put them on in a certain order depending on how much holdover time we want for that de-icing. And this, you'll see a couple questions in the ADX about de-icing fluid. You know, in what order should the de-icing fluid be put on the aircraft? You know, who gives a rat's ass? Memorize the answer and move on, right? We aren't out there de-icing the airplanes ever. I don't think they'd ever trust a dispatcher to go and do that. But supposedly we're supposed to know. Okay. Aircraft airspeed is an important non-meteorological factor which determines icing type and severity. The rate of supercooled water droplet impact increases with airspeed, which acts to increase ice accumulation. But this is counteracted by the increase of airframe skin surface heating due to friction. Okay. Typically, airframe icing is negligible at speeds above 575 knots. Crazy. So commercial jet aircraft are generally less vulnerable to structural icing than light turboprop aircraft. This is due to their rapid airspeed, powerful de-icing equipment, and tendency to cruise at higher altitudes where temperatures are typically too cold for icing. Conversely, light turboprop aircraft are more susceptible to icing because they are typically low and slow, where icing is more common. Flying into clouds, you're going to get ice 99% of the time. Just because clouds are typically high enough that the temperature drops below that, 10 degrees Celsius.
So even passenger jets that typically don't get ice at the 575 knots, flying in clouds, still gonna get ice.
Well, typically, yeah, commercial airliners, it doesn't mean that we're not susceptible to icing. It just means that when we're cruising, we're typically not going to even worry about ice. We are going to worry about icing, though, on takeoff and landing. Okay,
Right.
that's where the killer is. That's where icing is super, super, super bad, because if there's a cloud in front of the runway, not only is it obstructing the view, but you're also flying through precipitation or visible moisture, and typically you're going to be below 10 degrees Celsius because of your altitude. So the only thing is that we have really good anti-ice on the aircraft, and so it's rarely a problem for us. But let's say that there's a bleed air MEL on the aircraft. which makes it so we can't fly into icing conditions. You know, we could be flying into clouds, and that could create an icing condition that the pilot can't handle. And then, next thing we know, he's crashing on the ground. So, my meteorology teacher in college, aviation meteorology, he was I don't know if I told you guys this story or not already. Anyways, he flew corporate jets, and their corporate jet that he was flying was fitted with boots rather than the anti-ice heated leading edge. And he said that there was an icing level at like 30,000 feet, and they were trying to climb to 32,000 feet. And he would, or I can't, maybe it wasn't 30,000, maybe it was a little bit lower. But anyways, the point is he said that they would climb, and the bad thing about the boots on these airplanes is that if you if you deploy the boots too early and there's not enough ice accumulated on it, what will happen is the you're still plowing into these super cooled liquid droplets, right? And you're still creating ice, generating ice. Well, what will happen is the ice won't break off the airplane, but it will start to form at that shape of the boot. And so you just created a bigger problem for yourself, because now you're not able to get that ice off the airplane, right? So he said that there was just enough of an icing condition to where they would deploy the boots, break off the ice, and they would be able to climb to like 31,000 feet, and then it would ice, and so they'd descend down to 30,000 feet, and then they'd break, deploy the boots again, climb up to 31,000 feet, and then they would ice. He's like, so we just kept doing this wave of climbing and descent due to icing, and we couldn't climb through the layer because they didn't have the anti-icing equipment on their plane. Kind of crazy. So the important thing for you guys to remember is that icing can happen anywhere and everywhere. Okay, we're not going to talk about carburetor icing. We don't care about mountain icing and blah, 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 blah. Okay. Icing, bad, and 10 degrees Celsius, visible moisture. That's what you guys need to know and take away from icing. Oh, and the other thing is, as a dispatcher, we can never dispatch into known or forecast severe icing conditions. Or, I'm sorry, known severe icing conditions. These guys will put out these icing segments. There's none right now. But what will happen is they'll have this, let's say that this area is blocked out, and it says like 46E. That's the segment number. Okay. And it says moderate to severe icing. Okay. Do you think there's going to be moderate to severe icing throughout that entire, 10,000 square miles or whatever it is? I don't know how far it is.
If it's in Montana, yes.
Well, it's not going to be everywhere. There's going to be isolated pockets of moderate to severe icing, right?
Okay.
So there may be widespread light icing conditions, but typically we're not going to see moderate to severe icing throughout that entire area. So here's the kicker. So if we see this box and it says moderate to severe icing, okay, we can still operate in it. It's a forecast severe icing SIGMAT. Okay. We can still fly through here. It's not a big deal. But if a PIREP happens, let's say there's a PIREP that comes out and says right here in this area there's severe icing at our altitude, we can't fly into that area. So we would have to tell the pilots, hey, PIREP just came out for severe icing over this area at this altitude, and we'd have to like redirect him around the known severe icing condition. At SkyWest, I know if there's a severe icing SIGMAT in Canada, then we don't fly in there at all. Like, even though it's just forecast, we will not fly into a severe forecast icing condition in Canada. Oh man, you guys tired of hearing me talk? I am.
Would you be offended if I said yes?
Not at all.
Tyler.
Hey, we're reading a bunch of what are these, aviation circulars or something? Yeah,
yeah.
AC. These get old.
Oh yeah. Yeah, I definitely get tired of talking about them. Believe me.
I'm impressed y'all have been reading them. They're a lot.
Yeah. They are, for sure. So let's talk about stability, instability, adiabatic process. Okay. Which is this next portion here. So I'll tell you guys right now, don't feel like you guys have to know the adiabatic process because there's a lot that goes into it. And it took a lot of schooling to even get any grasp on what the hell they were even talking about, how to figure it out, things like that. Okay. The important part of this next section is that you remember that 2 degrees per 1,000 feet, 2 degrees C per 1,000 feet. Remember that. Memorize it because that's how we figure out what we call ISA, what we use in performance charts for flight planning. Okay. So let's watch this video and then we'll move on. Oh my gosh. Here we go. All right. Everybody watch that 10-minute video and we'll jump back on. Well, that video ended weird.
Yeah, it did.
I like that guy's accent.
There's more if you go like 30 seconds forward from that, just silence.
Okay, I'll give you guys another 2 minutes before I interrupt you again. So what did you guys think of that video?
I got it at first, and then it just started adding more and more different components to it, and it just kept confusing me more and more.
Yeah. It gets super confusing. Yeah, that's why we don't talk too much about it, because We just don't want to add confusion to you or for you. Remember 2 degrees per thousand. That's pretty much all you guys need to know. You guys saw how the adiabatic collapse rate, when it's the dry adiabatic collapse rate, it will continue to climb and climb and climb till it reaches that saturation point, right? Once it reaches saturation, then once it reaches saturation, it forms a cloud. And then you have the wet adiabatic collapse rate that will continue to climb, right? Because as you're creating that condensation, you're losing energy. That's why it's the moist adiabatic collapse rate. And as it continues to cool, then it runs out of energy, and that's the top of the cloud, right? That's pretty much the long and short of stability, instability, frontal, like convergence, and all that crap. But we're really concerned about that standard lapse rate because we use that to find our, like I said before, ISA, which is the international standard. Or, I'm sorry, stands for International Standard. Bleh. Atmosphere. There we go. Yeah. ISA, International Standard Atmosphere. So as we climb in elevation, it gets colder at 2 degrees per thousand feet, which we say is our average. And when we find out the temperature, the actual temperature at that, then we can figure out how cold or how much colder or hotter we are than standard, because our engines are built to a standard. Does that make sense? So if it's colder, it performs better. If it's warmer, it doesn't perform as good. So that's what we use adiabatic collapse rates for. But all kind of interesting. You guys can just eat your heart out on that on your own time if you want to. Personally, I've done enough. With it in my lifetime that I'm good. So if you guys want to learn more and you want to become pilots where it actually starts to count, go ahead. Turbulence. Here we go. So causes of turbulence. Turbulence is caused by convective currents, obstructions to the wind flow, and wind shear. Okay. So rapid changes in direction or speed is wind shear. Wind flow, meaning, or obstructions in wind flow, we call this, we typically, mechanical turbulence. We'll also see it called, there's another name for it. I'm trying to come out with it. Oh my gosh. Anyways, it's like when you're really low to the ground. That's typically when we see that mechanical turbulence or the obstructions in the wind flow. It's when there's a mountain or...
You're talking about ground effect?
No. Ground effect isn't turbulence related. Ground effect is just like... It's like structural turbulence or something like that. I can't remember the actual name of it. Oh my gosh. anyways, it's caused by, like, when you get lower to the ground, you get turbulence from the wind hitting the buildings, the hangars, whatever structures are in the immediate area. You get a little buffeting. Can't remember what that's called for some stupid reason. Anyways, so it can be by buildings, it can be by mountains, it could be by like trees. There's lots of things that can cause that mechanical turbulence. And then convective currents, that's the thermals, rapid rising of air. So convective turbulence is turbulent vertical motions that result from convective currents and subsequent rising and sinking of air. So these are those pockets that just form where there's warm, the ground is warmer in one area than it is in another, and creates these pockets of warm air, and that's what causes our turbulence. So those rising pockets of air. Okay. The hotter it gets, the more turbulent it gets. We'll also see a lot of turbulence, convective turbulence, near thunderstorms. And thunderstorms are usually, the way they become thunderstorms is usually by the heat, right? It creates that really convective cloud, the towering cumulus cloud, and that convective activity near or in that cloud is what causes that convective turbulence, because there's a lot of really, really hot air rising super quick, and it creates that convective swirl of air. Okay. The cloud top usually marks the approximate upper limit of the convective current. Pilots can expect to encounter turbulence beneath or in the clouds, while above the clouds, air is generally smooth, right? Because it loses all of its energy at the top of the cloud and just kind of dies out. Cumulonimbus gives visual warning of violent convective turbulence. You can also see, there's a good picture. This guy's in trouble, this guy's not. This guy right here, deep trouble. This guy, not so much, he's above it. But you can experience turbulence just flying near these clouds as well. I mean, you don't have to fly in the cloud. It's going to be more turbulent in the cloud, but due to, other factors, we may have turbulence in the vicinity of those clouds. When the air is too dry for cumuliform clouds, convective currents can still be active. This is called dry convection or thermals. Pilot has little or no indication of their presence until encountering the turbulence. So we also call this clear air turbulence. Okay, when we don't see clouds and when we see clouds, we can just expect turbulence, and the pilots will throttle back to that maneuvering speed we talked about. But sometimes they'll hit those rough patches of thermals, and there will be no indication of turbulence. We call it clear air turbulence. Okay, we see this a lot, especially in the summer, where a PIREP will pop up saying, hey, clear air turbulence over this area. Not a cloud in the sky, but they're expecting, moderate turbulence. So mechanical turbulence caused by obstruction to the wind flow, such as trees, buildings, mountains, so on. Obstructions to the wind flow disrupt the smooth wind flow into a complex snarl of eddies. Okay. Rotor wash, super bad. Used to piss me off so bad when I was flying because I flew at Bountiful Sky Park a lot. And anybody that's flown into Bountiful Sky Park knows that there's typically a lot of helicopters practicing at that airport as well. And helicopter pilots are stupid. Let's just start off with that. They have this nifty little aircraft that can land virtually anywhere. And where do they want to sit there and practice hovering? Not over the taxiway, not off to the side of the runway, but over the runway. Okay? Or right next to the runway. I'm talking like right here. Even Army helicopter pilots will practice right here. And it's really irritating because you come into land and like a Black Hawk helicopter, I got this at South Valley Regional as well. A Black Hawk helicopter puts out a lot of rotor wash, and when you come into land and that jackass is sitting, excuse the French, is sitting next to the runway and you hit that pocket of rotor wash, like your plane wants to flip over on you, and it is scary. Like it sucks bad. But yeah, so basically it's just caused by wind hitting a surface and then tumbling, not flowing smoothly over it. Mountain wave is another form of mechanical turbulence. Mountain wave, it's like a roller coaster ride. Kids love it. You got this mountain here. You got the air coming up over the top, then descending rapidly, adiabatically. And after the mountain, you'll see these long waves, or you won't see them, but you'll have these long waves of turbulence called mountain wave. And you'll you will ascend like 200 feet really quick, and then you'll descend like 400 feet, and then you'll ascend, and then you'll descend, and then you'll ascend and descend. And it literally feels like a roller coaster ride at Lagoon or Disneyland, if you guys haven't been to Lagoon. Some indications of mountain wave turbulence. You'll see Cirrocumulus standing lenticulars. You'll see the Alto Cumulus standing lenticulars. Or you may see what we call a rotor cloud. Rotor clouds are also one of those ones that we're going to see in our METARs. Rotor clouds, bad, 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 bad. Okay. Like it shows here, the air is coming up and over the mountain, right? And as it comes back up, it swirls. So it turns into like an eddy in a river, right? You get a really strong eddy. That's what a rotor cloud is. It will flip your plane in a heartbeat. But they're just as much an indication of turbulent mountain wave turbulence, right? So you get a rotor cloud, and then you have these alto cumulus standing lenticulars. You know that you're going to be experiencing mountain wave turbulence on the leeward side of that mountain. Okay, does that make sense? Everybody catch that?
Yeah.
Okay. There you go. There's the really choppy, nasty looking rotor cloud. Here's our alto cumulus standing lenticulars. And at a higher altitude, we have our cirrocumulus standing lenticulars. So wind shear, this is what we get a lot of going into Aspen. you know. You'll have wind going quickly one way, and then you'll go through this weird pocket of nothing. Like all of a sudden the wind will just kind of like die, and then the wind will reverse quickly. It may change direction, it may change speed, it may be a combination of both. But either way, what happens is pilots crap their pants because they typically experience this wind shear at low altitudes on approach to a runway to land. So wind shear is super dangerous. We talked about runways. When you're landing at a runway, okay, typically the wind is coming this way. You've got a headwind, right? If you have a tailwind, all of a sudden, rather than producing great amounts of lift, all of a sudden the tailwind will slam you down in the ground. Like you'll descend a lot more rapidly. So if you're not expecting it, it could be deadly. You could end up, extremely short of the runway. Okay. Sometimes we see turbulence when we have, or wind shear when we have inversion. And basically what happens is we have a warm pocket of air. If you live in Salt Lake, you know exactly what it is. So cold air, our standard atmosphere as we climb, we're losing 2 degrees Celsius per 1,000 feet, right? Well, with a temperature inversion, we get cold, 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 and then all of a sudden we hit a pocket of warm air. Okay. So what's happened is a warm vessel of air has moved over the top of a cold vessel of air and trapped it, basically.
Kind of like a blanket, right?
Yep, exactly. So temperature inversion, it'll be really cold down here on the surface, like -10 degrees. You get up here and it'll be where it's supposed to be colder. Get above the inversion and it'll be like a +10 degrees. Used to happen to me all the time when I would go snowboarding, get up out of the inversion, and it was like I would prep with like my really heavy snow gear, be all ready for it, and I would get up to the resort and I'd be shedding everything and putting it in my bag because it was just way warmer up on the mountain than it was down in the valley. So clear air turbulence, typically higher altitudes, 20 to 50,000 feet, turbulence phenomena occurring in cloud-free regions associated with wind shear, particularly between the core of jet stream and the surrounding air. It can often affect aircraft without warning. Clear air turbulence frequency and intensity are maximized during winter when jet streams are the strongest. So, yeah. Man. And here's a super important thing to remember about turbulence. So how an aircraft will respond to turbulence varies with intensity of the turbulence, aircraft size, wing loading, airspeed, and aircraft altitude. Okay, let's apply this practically. We have Grandpa over here in his Cessna 172. And he's flying along. And all of a sudden he says, severe turbulence over this area. Okay, he hits this pocket of air and he says severe turbulence. So all of a sudden a pirate pops up and it's like severe turbulence. Okay. We have our, heavy CRJ come fly through that same pocket of severe turbulence at the same time. He's going to be reporting light turbulence. Light to moderate, right? And that's due to the size and weight of his aircraft. Okay. What may be severe turbulence for a smaller aircraft may be light or moderate to a bigger aircraft. Think of like an aircraft carrier versus a tug out on the ocean, right? A tug, a 40-foot wave on a tug, you're done, right? You're just going to sink, boat's gone, whatever. But on an aircraft carrier, the deck may pitch 1 to 2 degrees. Like it's negligible when you're riding in the aircraft carrier because the aircraft carrier is like 10,000 tugs in size and weight. Right? So it's the same thing. Like waves in the ocean, the bigger the boat, the less effect it has on the boat. In the air, it's the same exact thing. The bigger the airplane, the less effect turbulence has on that aircraft. So remember that when you're dispatching and all of a sudden one of those severe PIREPs pops up in front of you and you get this warning, severe turbulence.
Will you know who the size of the plane of the individual who reported it?
Yeah, so
Oh, you will?
Yeah, it tells you the type of aircraft in the PIREP. It tells you the type of airplane that experienced it. So, so you may see like a Learjet or like, a 737, right? If it's a 737 and he's reporting moderate turbulence, we can expect moderate to severe turbulence in a CRJ. So, I mean, it just depends on the size of us, and it always shows us what aircraft. Let's see if I can pull some up here.
Yeah.
1 second. Sorry, I'm trying to find the info to get to the PIREPs.
I know Aviation Weather .gov has PIREPs on it.
Yeah.
Go.
This one's better though. This is a little bit better of a software here. Okay. So here you go. Oops. So what the? May have to pull it up on text form. Let's see. What city is close to any of those? Okay. Phoenix has some too. All right, so this is a Phoenix upper air PIREP. Okay, so Phoenix upper air. This means over. So this is the location where the pilot experienced it. So PIREPs are submitted by pilots. It stands for pilot report. So this pilot was over, well, he was near the PXR VOR off the 200-degree radial 15 miles out. Okay. The time that he reported it was 0040 Zulu. Flight level was 34,000 feet. Here's the type of aircraft, okay? E-75L. E-75L is our E-175 Embraer. So this is what SkyWest flies. It was probably a SkyWest pilot that reported this. Okay, he's reporting turbulence, moderate chop, and the remark. This remark doesn't matter. But yeah, this right here is telling us what type, and it's required in every single PIREP that's submitted, is the aircraft type. Okay. For that reason, to tell us, does this apply to us or does it not? This one for sure applies to us because that's what we fly, right? Oh, scheiße. So yeah, he's reporting moderate chop turbulence. There you go. That's what the PIREPs look like, and we're going to talk about this in the coming days, probably next week. So we'll start teaching you guys how to decode these PIREPs. But yeah, any questions?
Will, as a dispatcher, will we be able to know? Like, I wouldn't like just know that that's comparable to a CRJ. I wouldn't just know that.
Yeah.
Will I have to stop and go Google it or what?
Yeah, sometimes you do. Sometimes, you see like a PY12 in there. No. Maybe that's a bad one. I can't remember all of them. What's the Pilatus PL aircraft? Pelican. There you go. You know, like sometimes I have to look it up. But a lot of times what you're going to see are commercial aircraft. So all of Boeing, it's really simple. If you see a 7.3, like you see a B-7.3, it doesn't matter what the last number is. If it's a 737, 739, 738, whatever, you know that it's a 737. A B-74 is a Boeing 747. A B-77, Boeing 777, you know. So Boeing's a pretty easy one to figure out. Airbus, very similar. Airbus, you'll see like an A19 or an A20 or an A32 or an A31. Like you'll see A38. So you'll get, the more you look at them, the more it starts to make sense. It's one of those things like METARs and PIREPs and NOTAMs. You have to look at a lot in order for them to make sense. And you'll get it. I mean, especially as you start working with them and looking at them every day.
Yeah. It
You
just
know?
becomes familiar then.
Yeah. But I think there's even a aircraft PIREP type codes. There's a list right here.
Oh.
So that'll help you, and you can even like hover over it and see what the airplane looks like.
Will you throw that in the chat box, please?
For sure.
Thank you.
So like I was saying, A319. Here's the Boeing. All your Boeing aircraft. You know, it's always designated like a 7.3, 7.4, 7.5, 7.6, 7.7, 7.8. You know that that's a Boeing aircraft. Cessna 172. There's Grandpa. But anyways, yeah, I would look them up all the time. If I didn't know what they were, I'd be like, what the heck kind of airplane is that? And you just do a quick Google search and you're like, oh, yeah, I should probably tell my pilot that he's going to have some turbulence coming up. Or sometimes if you're super busy, you just forward the PIREP over to the pilot and let him decide if it's applicable or not.
Oh, that makes sense.
So anyways, I've let you guys starve for a really long time. Sorry. Forgot about lunch break. So I'm going to, gosh dang it. I am going to let you guys take your 30-minute lunch break.